So the today topic is automated optimization of a prismatic light guides using Ansys Speos and Ansys optiSLang. So in this session, so the main agenda of this session is introduce you to through the Ansys Speos software and some of the applications what you can do it with it, and using the Ansys Speos, how to create a simple light guide and one created light guide which is used as a daytime running lamps. So that kind of a light guide, how you can optimize it while integrating that Ansys Speos tool with optiSLang, another tool. So this tool is actually a optimization tool. So within using that tool, like what you can do, like sensitivity analysis, how you can optimize your structure, we'll all see in this webinar. So myself, Jaya Krishnan. So I'm an application engineer working for Ansys from ARK Info Solutions. So this is the agenda. So first I'll give you a brief introduction about the Ansys portfolio and then I'll take a small walk around through the Ansys Optics portfolio and then Ansys Speos, and then I'll introduce you to the Ansys optiSLang software. After that, I'll be showing some of the demos, like how to create a light guide in Ansys Speos and how to prepare the created light guide for the coupling with Ansys optiSLang and how to perform this process integration in Ansys optiSLang, and how to do the post-processing results that we got it from the Ansys optiSLang. So this is what we will cover during the session. So this is our Ansys product portfolio. So we are covering almost all the engineering physics that starts from electronics, semiconductor, structures, fluids, optics, acoustics, 3D design, and all. So over the years, we have many companies or industries, researchers are trusting Ansys for their research or for the product manufacturing. And one more thing is digital engineering powers faster time to the market. 50% of development, 50% of reduction in development time with automation of analysis and more. So 10% of reduction in physical prototypes and upfront testing, and then 30% increased use and reuse simulation. You can unlike a physical prototype, you can keep on using it. So these are the complete Ansys comprehensive solutions for different physics that we are offering. Today, we will be talking about a particular physics called optics, and within optics, what are the tools that we are offering for the comprehensive end-to-end simulation. And then in the tool, we will be talking about one particular tool. So the Ansys optics. So we all know that optics is nothing but it is a branch of physics which deals with light interaction with the matter. So when light interacts with matter, it will exhibit different phenomena. So various phenomena based on these different phenomena, like we are using these light matter interaction in different applications, starting from the nano level to the system level modelization. Like one such example, we can say it is a camera. So the camera is having a sensor as well as a combination of lenses, as well as it has to work with the complete electronic as well as the things. So in order to offer this end-to-end multi-physics and multi-scale simulation platform, we have Ansys Lumerical. So the Ansys Lumerical is nothing but it's a photonic component modeling tool as well as circuit simulation tool. So within which you can model optical fibers to do the numerical aperture model analysis and all, and then you can create waveguides, sensors, micro lenses and all. That is actually nano level, like when light interacts with the wave sizes of matter which are comparable to the wavelength of the light. And moving on to the macro size, where this time we will be talking about the matter sizes is in the order of millimeters and in the order of centimeters, like lenses, mirrors, prisms and all. So for this kind of simulation, we have a dedicated tool called Ansys ZMax. So Ansys ZMax is an optical imaging as well as illumination design tool. So ZMax is a gold standard tool when it comes to optical imaging systems. So within which you can design your optical design as well as can validate its performance. Apart from that, you can optimize it, you can apply the tolerancing analysis. And you can also furthermore, you can take your design to one more level, like multi-physics simulation, where you can do the structural and thermal analysis with your tool. And finally, to the macro level, to the system level. Here we will be talking about only the optics. So anyway, the optics has to work with some other components like optomechanical devices, like optics has to work with some mechanical components, electronic components, or it has to work in the real world environment. So how to model that kind of a things. So Speos offers you this kind of leverage, like where you can integrate the 3D environment. So by integrating, so you can see how your optical system is performing in the real world. And along with that, human vision, we have the human vision capability so that you can understand how your optical system, like how the humans are perceiving it. So, and much more. So in this presentation, I'll be giving an idea about what are Speos and what are all the key capabilities that Speos is offering. Speos. So Speos is actually nothing but it's a in a sentence, how can we say it's a software? It's a light and human vision simulation software. We want to visualize the light through a human vision. So that's it. So that is the basic idea of this particular software. You can create a CAD design and then you can visualize its light behavior using a technique called ray tracing, and then you can do the light simulation. So you can virtually test all your lighting systems with different analysis techniques. And you can, once you have done it, you can evaluate whether it is up to the mark or if it is not, and you can optimize the performance of your systems using the built-in tools that is available in Speos. And then you can also do the lit and unlit appearance for early detection, design issue detection. Let's say like the real world environment, like with lit and without environment, how it is actually appearing. So this you can do it for an early design issue detection. So the main goal of using any simulation software, not only Speos, any simulation software is to reduce the time and cost to the market with zero prototype. So you don't have to make a prototype, like you just need to make all the prototypes virtually, and then while making a prototype, it should be the final product. So that is the goal of Speos. So these are the Speos key capabilities. It is a light modeling and analysis tools. It has a large pool of material data and as well along with coatings and all paint. Every material database is there within which. And Speos have a key capability called human vision, which allow you to pierce your optical design through a human vision. And we have a optical design tool which allow non-optical or else like non-CAD designers to design the optics very fast. And optical sensors, like we have a different optical sensors within which are integrated within Speos, and you can do the straight analysis in Speos. And we have a broad spectrum starting from ultraviolet to the far infrared for various applications. And we have a local optimization tool, and along with we have another tool called optiSLang. So optiSLang can interact with this and you can optimize your design. And in order to accelerate the simulation, we have the HPC, high performance computing capability, as well as the GPU computing capability. And automation, like we have Python integrated with Speos, so that you can write a code on your own to automate your simulation, or else like you can create a custom workflow. So, Speos, what you can do is like you can simulate the complete optical system, like so Speos has a motor correlate ray tracing. So it actually allows you to identify any light contribution to our optical system. Like let's say you have an optical design. So a light contribution not only because of the source, it could be due to some additional material property or something like that. So Speos will allow you to see that. So from any light source through advanced optical scattering materials to the sensor, you can completely do this ray tracing. So, and we have a feature called light path finder. So within which you can you can look at the image. So it will allow you to see how the rays are traveling through the optical components, like where it is actually reflecting. So the what kind of color of the rays indicates the wavelength as well. So in which it will allow you to see the trace your optical path. And then optical design optimization. So it helps to it reduces the gap between the optical engineer as well as the CAD engineer by automatically optimizing the optical performance. So what it will do is like Speos has the capability of dynamic CADling along with while optimizing it, it will automatically optimize your CAD based on the criteria, evaluation criteria that you have given. So you don't need to once you got the optimized parameters or like evaluated the performance, you don't need to redesign based on the optimized parameters. Speos will do on its own. You just need to provide the like optimized design to the the further product development. And by doing so, it is actually shortening the engineering development by increasing the product engineer productivity. And for optomechanical system, you can also process tolerance statistics. So, and then human vision. So on your right hand side, you can see an image. So which will allow you to understand like what Speo's human vision means. So it will actually simulate the perception of light, colors, and materials in your optical imaging system. So this is one simulation. Like let's say a human is seeing through a car window while he's driving at a night light. So this is the actual simulation result. While applying a human vision, what you can see is a 20-year-old person is actually visualizing this scene like this. A 55-year-old person has he is having some other additional glare effects, and a 60-year person he is also experiencing some additional glare and grain. So by taking advantage of this particular Speo's human vision feature, what you can do is like the perception of colors and materials for harmony, texture, light, uniformity, and brightness. So it will ensure visibility and legibility, considering glare effects and time adaptation. So these glare effects are very important, like when you are having a particular target audience, and also it will ensure safety, improve visual comfort, and reach perceived quality targets. In market, you may be designing a product which could be targeting certain age group of people. So at the time it will be so in that case, human vision will add a more value to your products. And then optical part design. So we have an optical part design tool, which is a dedicated geometry modeling tool within Speos. So it will automatically generate the particular optics. So for example, creating light guides, optical lenses, and optical freeform surfaces, or else like honeycomb lenses is not at all easy. So it has a lot of different parameters. So while you are designing by CAD, it will take a lot of time. Also, while optimizing, it will create a lot of problem. It will create a difficulty. But using this optical part design, you can able to generate a light guide on optical lenses and surfaces or like anything in a minute or like in seconds. You just need to define certain parameters initially, and Speos will automatically do it for you. So this is actually very much easier for non-experts, those who are really new into the system, and it will also help you to help you when you're doing the simulations. So what we are going to do is we will be using this particular feature while designing our light guide in the upcoming slides. And regulation standards. So when we are talking about the automotive industry, like where headlamps, DRLs, like tail lamps or manufacturing, so they need to pass a certain regulation standard based on the government. Like there will be some. So Speos allow you to use the measure these regulation standards based on the intensity or else the radiance map. So this is so we'll be seeing this as well. And multiphysics simulations. So whenever you're designing an optics, so it doesn't mean it has to be optics. So it can have a thermal impact due to some external thermal environment. Maybe your system can affect, or else like due to the housing, or else like mechanical components that is housing or optical systems. So you may there is a slight chance of the optical performance. So you can do this multiphysics. Like earlier, I have shown you the complete Ansys product portfolio, right? So these Ansys optics tools, like Ansys Speos, can interact with other tools as well. So for a multiphysics simulation, where you can anticipate thermal as well as the structural impact on your optical performance. And then in order to accelerate the simulation, and quickly evaluate our systems at extremely high resolution, we have HPC, cloud computing, and all. So you can see on your here, this is actually one simulated thing from Speos. So these are some of the capability that it requires to simulate this. So if you are having a huge HPC cluster like 720 cores, you can do it in a night 10 hours. If you are having HPC cluster 24 cores, sorry, 250 cores, it will take a weekend, 2 days. Or else like small cluster, 120 cores, week, 5 days. If you're having 60 cores only machine, so it will take 30 months. So I'll show like what kind of simulation it is. This is actual simulation that will take. This is the complete simulation. So this is, they have done it in Speos using the HPC as well as the cloud computing capability. So from this itself, you can see the HP, like if you have this capability, it will be really faster you to do your simulation at extremely higher resolution and as well as higher faster rate as well. And then Speos applications, like Speos has a wide range of applications in different industries, in automotives, high tech, aerospace and defense, general lighting, white goods, also in biomedical and medical industry. So in if we are particularly talking about automotive, so these are some of the applications: exterior lighting, interior lighting, colors and materials, heads-up displays, ADAS, like autonomous driving assistant vehicles. Nowadays, like these systems are there. Like one example, we can see Tesla. And then in high tech, like AR, VR headsets, so where you have to integrate the optical elements and camera module, displays, projectors, and all. And in aerospace and defense, you have to do the radiometric analysis where you will be covering the broad spectrum, like up to far infrared, atmospheric effects, night vision goggles, high power lasers, and all. So all these things where Speos could offer, like in aerospace and defense. And when it comes to general lighting, indoor lighting, outdoor lighting, street lighting, so you can design the light source as well as specialized lightings in white goods, like where the goods are like white, like colors and materials, product configurator, visual ergonomics, illuminated button and all. So these are some of the wide range of applications where Speos is being used. So next, till now, like I have shown you like what some of the key capabilities of Speos, Speos, HPC and cloud computing capability, and where Speos can be used. Now, the another tool that we are going to use in this in these demos, the upcoming demos, is actually Ansys optiSLang. So what is Ansys optiSLang? So Ansys optiSLang, it's a software or a framework, we can call it as a. It's a process integration as well as a design optimization tool. Just give me a moment. Yes. Uh, so it'll work along with the simulation tool, like other Ansys physics tools, or it could be a structure tool, or else like it could be a optics tool, fluid tool, anything. So, and based on that, so we can create a workflow and you can automate it to workflow. And also you can use this Ansys optiSLang for studying the sensitivity analysis. You can optimize your system based on the objectives that you are giving, and then you can do the robust design analysis as well, like how the real world tolerancing is affecting on performance of your system. So this is what optiSLang can offer. So why do we need to do Ansys optiSLang? So this is what it will do. It will calibrate your device based on the performance criteria that you are given. It will do. We can do the sensitivity analysis, optimization, robust evaluation. So it will create the meta models and all. So you can do a process integration within which, and these are some of the things that you can do it with the Ansys optiSLang. And this is kind of a workflow. Like, so the first thing is to automate the create a workflow with the physics tools, and then you can also publish those workflows as a web apps. And then once you have created a workflow, the next thing will be parametric variation analysis. Based on the parametric variation, you will be doing analysis to your uh, uh, design. So the first one will it be sensitivity. So it is need to understand your design. So what parameters are affecting your design? So which parameter is affecting like offering more sensitivities? By doing so, you can reduce the complexity and generate the best possible meta models. So meta models are nothing but they are actually different multiple designs of your physics, the simulation tools that you're using. If I'm using a light, if I created a light gate using Speos, so while doing the sensitivity analysis to create a different number of possible meta models, like let's say 300 or 200. And by comparing all these, it will give you a, like a tool, sorry, it will give you a best design. And once you have done the sensitivity analysis, you can go for the optimization. So it will help you to optimize your system based on the criteria that you are giving. And after that, you to understand the design quality. So design quality. So obviously there is a fabrication as well as the assembly tolerances whenever you're talking about the optical design system. So you need to understand the design quality. So using this robustness analysis, it will allow you to ensure the design robustness as well as the reliability. And then you can calibrate the model based on the sensitivity analysis as well. So by doing so, you can understand like which model is very much important and best fit for the simulation and measurement. So while going through the design and while setting up the workflow, it will be really easier for you to understand. So like the conventional simulation workflow, let's say this is a traditional approach. So you have a input values, you'll be having a CAD file generation. The next thing what you have to do is you have to feed it to there will be human involvement. He has to take the file and you have to input into the another tool, and then again there will be a man in loop, and then he has to feed it into Ansys Fluent, and then for post processing again a man has to take the output and he has to post process it. So this is what the complicated conventional simulation workflow. But obviously this will increase the time to market, so there will be slow time to the market. But due to optiSLang, there will be an automated workflow. So the workflow will be like this. You just need to define the parameters and all like input values, and then it'll do automatically the post processing. It will do the simulations, like what are the things that you are giving. It will do everything so quickly, and you can easily automate and integrate with any application, like especially any Ansys applications. So these automated workflows are reusable. So, but you can easily modify these workflows as well. Like on double-click on it, like you can modify, like let's say you want to change something settings, like or else like you want to add new parameters, you want to add like different criteria to it, like you can do it. Or else like you can you other not only with the Ansys apps, like there are some scripting apps like Python, MATLAB, like you can use those those apps for like post processing as well. You can include those apps, include the workflow. So this is an optiSLang or like automation, like as well as the complete optimization. This is how that integration workflow schematic will look like. It can have a number of branches and like so earlier as we discussed like sensitivity as well as the optimization, robustness analysis, we'll be talking about three things. One is how to set up a normal like workflow between Speos and optiSLang in optiSLang, and then how to do the sensitivity analysis and how to analyze the sensitivity analysis results, and after that how to optimize your system based on single as well as multi-objective optimization. So this is what we will be doing. So what is sensitivity analysis? So it is nothing but it's understand the most important input variables. So you will be providing some of the parameters, design parameters. So based on it, like you will be giving a performance criteria. Let's say I have a light guide. So it is giving certain luminance. So my luminance has to be maximum, and just change the shape of my light guide. So how your shape is actually affecting this particular performance criteria. So this is what the sensitivity analysis will allow you to do. So based on the parameters that you have given and the criteria, it will create the number of different meta models. The meta models are nothing but different designs of your simulation, and then it will analyze all the simulations and it will give you certain post-processing results. So based on those results, you can identify which could be the better one and so what thing that you can do and all. So this is the sensitivity analysis. So and the next one will be the optimization. So in optimization, you can do a lot of things. So what you can do is you can either add one objective. Let's say my only objective is so attain average uniform illuminance. If that is my objective, so that will be a single objective optimization. Let's say I also want to reduce the RMS contrast. Along with it, my maximum brightness has to be like this. So if you are having multiple objectives, so that will be the multiple objective optimization. So you can do optimization with based on either ways. And so Ansys optiSLang will integrate with all the physics tools that Ansys is offering. So it can interact with fluids, structures, electromagnetics, semiconductors, embedded software, opticals, and all. And next, we'll be talking about we'll be going into the demo. So our particular demo is DRLs, I mean daylight blending lamps, which are like specifically into automotive industry. So these are some of the automotive lighting development areas. So if you look at this image, you can understand where the development are being happened in the automotive lighting industry. So dynamic lighting scenarios and animations, layer lamp design and lit appearance. So welcome lighting optimization, sunburn and defogging. So heads-up design analysis, ambient lighting design, and apart from that, like human factors and perceived quality assessment with the human light vision. So these are some of the development areas uh, in automotive lighting industry, and how Ansys is offering some of the comprehensive solutions for automotive lighting. When it comes to interior, you can do the visual ergonomics, lighting design, heads-up display, as well as perceived quality assessment. And when it comes to exterior lighting, you can model the exterior lighting, welcome lighting, lamp lit and unlit validation, dynamic light testing design, virtual night drive, headlight designing, sunburn analysis, headlamp defogging, virtual EMC analysis, all these you can do. So these are the comprehensive solutions that Ansys is offering for automotive lighting industry. And here we, since the DRLs is made up of light guides, so here we'll be discussing about the light guide. So light guide is nothing but it's a pipe, optical pipe, where we'll be launching a light into the light guide, and a ratio or a part of the light will be extracted into it, out of it using a prism. So with the prism, so it is really difficult to extract the light out of the light guide. So here we will be talking about the prismatic light guides only. So these are the different features. So using these different features, you can extract the light out of a waveguide, like prisms only, like gaps. You can increase the gaps between the prism, milling, and then like a variable axis. You can remove the prisms, create a like vacancy over there. And the light guides are being used in different applications, like in side mirrors, dashboard, door panels, consoles, footwell, a cup holder, rear lamp, as well as DRLs and all. So how to create a light guide in Speos? So this is a light guide, as you can see. So we are launching a light into the light guide, and the light is traveling into inside the light guide using a phenomenon called total internal reflection. So the incident light has to be greater than the critical angle so that it will be to the total and inter reflection. So by one end, we will be adding a prism, okay, so that it can come out of the light guide. So what we will be doing is we will be based on the prism design. So the number of light rays that it is emitting out of this will be varying. So this is the way to optimize the prismatic light guide as well. So if you don't have the prism or like any other designs on the other side, so you cannot extract the light out of this light guide. So that is the basic idea. So now we will see how to create a simple light guide in a Speos. So let me walk you through the Speos interface. So this is the Speos interface. You can see different tabs for designing, display, assembly. So Speos is integrated with a CAD software called Ansys CAD software called SpaceClan. So apart from this light simulation and the design tab, so the optical part design, so all the tools are related to CAD only. So Speos is a CAD agnostic tool. So whoever is very much versed in CAD, so they can easily design anything here and they can do the optical simulation. So not only with the SpaceClan, so for along with NX, Siemens, and Creo, we have Speos as well. So instead of SpaceClan, so along with NX, we will be having optical simulation, light simulation tools, and along with Creo, we have a light simulation tools. Speos is offering that as well for designers who are using NX, Siemens, as well as Creo for their CAD development. So it supports n number of CAD files, like almost all the CAD files Speos is supporting, like wherever you're designing your CAD. So you can directly import it into Speos. You don't need to convert into a specific Speos format. You can directly import it and you can start working on the design. So now I'll tell you how to create a simple waveguide using an optical part design. So while I was showing the presentation, you may have seen this optical part design. Like I was talking about the dedicated geometry modeling. So it is easy for a non-experts. So that's what this optical part design tool is. So go here, you can see different optical part designs, like for complex things like parabolic surface, polyellipsoidal reflector, different optical surface where you can create rectangulars, circular stripes, freestyle rectangular and all, and TR lens, projection lens, freeform lenses. And when it comes to optical lenses, like where these lenses will be used in the reflectors or reflectors of the headlamps. So you can create it, and light guides, micro strips, and heads-up optical design. So these are the main features which are available in the optical part design tool. So using the light guide of this particular design tool feature, we'll be creating a light guide. So in order to create the light guide, you need a light curve. So first I'm going to draw a curve. So go to the sketch. Here I have an option to draw a curve, explain. Yes. So now I have created a curve. So this is my light curve. So I'm going to generate the light guide through using this line as my light curve. So go to the optical part design. If you click on light guide, you can see, left hand side, you can see the design, layers, texture, group, and simulation tab. So in the design tab, you can see the light guide is appeared here. And on your right hand side, you can see a definition tab. So the definition tab is nothing but it contains the list of properties that you can apply for a light guide. So here you can see the type is actually circular, the diameter of the profile, and then like this is for prism orientation and this is for prism geometries, as well as the other general distances. So the first thing is I have to select a guide curve. So this is my guide curve. I have selected it. And the next thing I have to select the optical axis. So I'll have selected the optical axis along the Z axis, and then I click compute. Yes. Now you can see the light guide has been designed. So it is very simple. So it didn't took that much. It didn't take that much time, right? So this is what Speos can do. And also, like while playing with the parameters, you can like, you know, what else I can do? Like, let's say I can add the control points like for these prisms, or else let's say the profile diameter is 6, right? Let's say 3. And again, click on compute. Now you can see the profile diameter has been 3 millimeter. Now we are having circular shape. So what I can do is I can either add a, instead of circular, I can add a rectangular or a square shape, or else I can create a prism only profile like this. So I click on prism only, I click on compute. Now you can see my light guide is only prism. You can see the light guide, light curve as well. Now let's say I have my light curve, right? So let's start with, I'm going to create one origin here. So what I'm going to do is I'm going to sketch. So let's create a rectangle. Now, what I can do is, instead of prism only, I can able to select a constant profile. So where this will be my light guide, and this will be my constant profile, and this will be my optical axis. You can see earlier it was a circular profile. Now I have applied a profile which is a square one. So I can apply a different profile as well. So in this way, you can create, you can play with the different parameters to design your light guide. So this is what Ansys Speos is offering when it comes to optical light guide design. So not only to the light guide design for different types of design, so you can um, use it. So this is about it. And now what we are going to do, the next step is, now you got to know like how to create a light guide and how to play with the parameters. So the next thing is, we have already one design, so which is for a DRL lamp, which is also a prismatic light guide. So we'll be analyzing the structure and we'll be using optiSLang along with Speos on how to optimize it. So let's go here. So I have already the file. So we'll be going to the headlamp light guide. So let it open. So this is my file. Okay. So this is my light guide that I'm having. See to the latest version. Yes, click on save. If you go to the simulation tab, you can see this is my complete simulation, like where they have applied materials to the light pipe, which means to the light guide, and along with other things, and they have added sources, and we have two sensors. So how we are going to optimize our light guide is based on two things. One is based on the intensity as well as the average radiance values, along with the, it has to pass certain number of rules in the regulation. So if you click on the intensity sensor, you can see we have offered certain templates. So these are the templates for analyzing the intensity as well as the illuminance for this DRL lamps. So we're using a standard regulation templates. So these templates are also available in Speos library. So whenever you're defining a sensor or creating a sensor to analyze your lighting system, so by using these templates which are available in the library, you can easily analyze the system's performance, like which should also meet the regulatory standards. So for both the sensor, so the intensity is for measuring the intensity, and the radiance is for measuring the illuminance, like how much light it is emitting. So we want to achieve a uniform illuminance, like the light has to emit uniformly across the entire waveguide, not here or like not here, like so it should achieve a uniformity. So that is one thing, and it also follow the rules for the pass the rules for the intensity. So these are the two things. These are the two constraints that we are having. Now let's everything has been defined already. So the one thing is we will be going to run the simulation. So this is actually a simulation, or let's run it. So let it run the simulation. So it won't take that much time since it is a smaller simulation. It is not a complex one. So now we got the results. So this is my light guide intensity map. If I click on it, so here is the intensity map. So if I click on here, we have an option called measures. If I click on it, it will show what are all the regulatory conditions or standards it has been passed. So I can click on this button to also see the grid view. Like the center value is the actual value at different points, which has been assigned by the templates across the light waveguide. So different points at the waveguide. So these are the illuminance, so the intensity value. So here you can see the minimum value that it can. So if it goes below this particular value, it will fail. Okay, so that is the idea. So now you can see all the values are not below this particular value. So since it is like that, it is given us it is looking like sorry, green color. It will be marked as green. Let's say now at this particular point, like the value is below 40, it will become a red color, which means it is not passed. So these are the rules. These are the rules which are set by these XMP templates that we have taken from the library for measuring the intensity, especially for the DRL lamps. So that is what it is. So all our rules are actually passed. So we'll be using these as well. So our design shouldn't fail the rule while we're optimizing it. And also it should achieve the uniformity. So that's our goal. So now let's close this and let's go to the radiance to see the illuminance. Now let's go to the luminance. So here also you can see here. So the RMS contrast is actually 0.75 as well as the area. I mean, the average illuminance value is around like 183 kilo candela per meter square, and the minimum and the maximum values are here. So if I click it here, you can here you can see it is around like 101 kilo candela per meter square. But if I go here at the other end of the waveguide, so it's very low. It is 26K only. I mean, instead of like in hundreds, it comes to 26K candela per meter square. So this is how the uniformity is across this light guide. So there is no uniformity. So from this itself, what we are going to do is, so in order to achieve the uniformity, what we have to do is we have to make this average value, as well as we have to reduce the average value like to the maximum across these values, and as well as the reducing the RMS contrast at all the points. So by reducing the RMS contrast, we could be able to achieve the uniformity. So that's what we are going to do. So this is our goal. That's what we are going to do. Now we have ran the Speos simulation. Now what you can do is, there are two ways to interact with optiSLang. So the one thing is, if you go here, you can see a button called optiSLang. So in order to use this, there is a plugin. So you have to install the plugin so that you can directly go from Speos to the optiSLang. So the one thing that you have to do is you have to publish parameters. So for example, let's go to the design. So now we know what is the criteria that we are going to do, what is our objective. So our objective is achieving uniformity, and the criteria is the RMS contrast has to be low, and it has to pass all the rules, which means no rule should be failed in the regulation. Along with that, the average has to be the maximum. Okay, these are the criteria, and we have a objective as well. So, and in order to achieve it, what is the degrees of freedom in your design? So the one thing is you cannot change your light, so that is very constant. So the other thing is you can play with the design parameters of your light guide. So that is it. So if I'm clicking my light guide, you can see there are different degrees of freedom. You have type, have profile diameter, direction, origin, like you can the different operation. You can change the refractive index, which means you can use a different material, or else like you can change these distances, like where the light guide has to start, where it has to end, like the prism thing and the prism geometries and all. So now what we will be doing is we will be taking care of these points, bottom trimming control points. So in the next slide, I'll show what these bottom trimming control points means. So we have taken 5 values. So from 0, so these are the 5 values that we are going to use. These are the only 5 values that we are going to optimize in the light gate to achieve the you better homogeneity across the light gate. So that is what we are going to do. So we have this control points, right? So whenever you want to use this parameters in the optiSLang along with to create a workflow, the first thing you have to do is you have to publish these parameters. So that is actually a kind of a workflow. So you can, if you go to the workbench, so on your right hand side, you can see a thing called publish parameters. So this publish parameters will be working as an input to the workbench as well as to the optiSLang. So click on it. Now you can see these are all the parameters that you can use as an input when you're using optiSLang. But here I'm going to take these control points only, trimming control points. So I have taken 5 points. So the 5 points here, these 5 points. And now if I go to optiSLang, click on simulation. So, and if I select this particular simulation and click on optiSLang, go to optiSLang, it will go to directly optiSLang and it will create a project. So this is one way. So the another way, it will be little time consuming and you won't be having a, you cannot see what it is actually the progress inside it. So it will create a workflow and it will create a project. But we are not going to do it. What we are going to do is we will be going to optiSLang and we'll be creating a complete workflow and what are all the things that like how we are adding the parameters, input parameters, how we are taking the results, and based on the results how we are setting up the criteria to optimize our structure and all, to optimize and do the sensitivity analysis. So that's what we will be doing it. So now let's go to the optiSLang. So you can see this is the optiSLang. So and before it, I would like to understand like what does this control point means. So let's go to this. So now we have talked about the light gate, how to, now you know how to create a light gate and all. So for variation analysis, which means like whenever we are defining different analysis, so it is always necessary to define which parameters that we are going to optimize or like change. And based on that, what are the responses? So here the responses will be mostly intensity and the radiance, especially the average illuminance, the RMS contrast, and the intensity rules that the regulation based on the regulation standards. So these are the design variables that defines the design space as well as the some of the other variables which is taking factor of this robustness, and it will be feeding to the solver, and then Speos generate results according to the inputs that we are giving, and we'll be having the responses. So these responses will be the criteria responses as well as these parameters will be the inputs. So these two will be the inputs and the criteria will be the idea of how the like a rule. So based on it, the optiSLang will perform. So so the light gate parameters that we have taken. So here you can see this is the light gate that we have designed, and so the trim control point is nothing but it is actually how much of the prism is out of extruding out of this particular light. As you can see, if the trim ratio is 0%, which means the entire prism is there, and if it is 10%, you can see partially cut one, and if it is 50, half of the prism is gone. You can see. So this is what the trim points means. So we have taken totally 5 points. As you can see across this waveguide, CP0, CP1, CP2, which means control point 0, 1, 2, 3, and 4. Okay, you can name it anywhere. Like let's say we are going to name it like this. And further, not only these parameters, you can also take multiple parameters like profile geometry. So what kind of type? So here it is circular. You can take a rectangular, different type of profile as well. And prism geometry, like where it is actually starting. So it is starting from here, but the light gate starts from here. So you can change these distances and what is the angle it is starting the prism and how it is ending angle. So all these things you can change, and prism milling bottom and top. So these are other possible parameters that could be the optimization parameter as well. So but here we are going to take the trimming of the control points. And once we have done it. Like this is what we will be doing. So we will be using Ansys Speos to create a light guide like this, and we'll be running the simulation to check the homogeneity as well as the ECE regulation. Okay, now we have done it actually. So the regulation pass is done, and we have taken the like values like average value, illuminance value, RMS contrast value, and all. And then we'll be creating a workflow based on the inputs, outputs, and the criteria, and then identify which input parameter is more important, like creating the doing a model by doing the sensitivity analysis. And then we'll be doing an optimization to identify the best design, like the one which has the best parameter to achieve the uniformity. So this will be the summary. We'll come to the later. So now you can see the initial design is having 0.74, as well as the average illuminance is around 183 kilo candela per meter square. Now let's go to Speos to once again take a look at the initial design. So this will be the initial design. Now if I click on it, you can see the average illuminance value and all, like the average and RMS contrast value. Now you can see the 2D view of a section. If you click it, you can see, so this is the length of the waveguide, 0 to 40 millimeter, and this is how the light distribution is there. As you can see, when the waveguide starts, where the LED is there, so here the candela, the light is too much. As you go, far from the waveguide, like longer the waveguide, as you can see, there is a decrease in intensity, sorry, illuminance. So this, keep this in mind. So we will be checking the same thing once we do the optimization as well. Okay. Now, if you go here as well, you can see, so the initial design is having a thing like this, and then we'll be seeing multi-objective optimization and then single objective optimization. We'll be having a multiple objectives while optimizing the design. Also, we'll be having a best design based on only single objectives, like only focusing on RMS contrast. Okay, that's it. So let's go to optiSLang, and I'll show you how to set up a workflow. I mean, how to integrate this process, set up a workflow between Speos and optiSLang for optimization as well as for the sensitivity analysis, and then how to do the sensitivity analysis, and then how to do the optimization. So let's create a empty project. Let's have a title like this. You can take any places where you want to create this. Let's say in this folder, let's say I want to keep it in the reference, select folder. So it will be like, initially I'm not going to give any name. Let's keep it like this. As you can see, it will create a group of directories based on this. Now we have created it. So on your right hand side, you can see the wizards, different wizards. So the solver is with wizard for creating a workflow. Sensitivity is wizard for is adding the sensitivity analysis, and optimization is for optimizing, and robustness is for including the robust analysis in this. First, we need to create a workflow. For this, create a drop it. So if you drop it, the solver will open different type of Ansys tools that it can access. So now here you can see Ansys Speos. So click on it. So if you click on Speos, it will allow it will let you search the light guide tool. So that's what we are going to do. We need to find the design like headlamp light guide. So let it analyze the structure. But keep on mind, you have to click on publish parameters and you have to select the parameters. What are the parameters that you are going to use, and then you have to save the file in the Speos, in Speos. Once you've done that, you can directly import that file. So it will take those published parameters as a input. Okay, keep that in mind, like unless you won't get it, like, so that is the main thing. It can take some time also, like and also while optimizing and doing the sensitivity analysis, so we'll be running nearly 100 or 200 designs, or like sometimes, like while optimizing, it will randomly take 4,000 designs. So in order to run all those designs, it will take a lot of time. So what we are going to do is, we are not going to run all those things. I'll show you how to analyze it. Like, I'll know how to set up it. If you click on it, it will run and create multiple designs, and based on it, you will get the analysis, like post-processing results. And I'll show how to analyze those post-processing. So that is very much important. Okay, now you can see these are the parameters that we have selected and published parameters in Speos. Now these parameters are here. So we have to drag these parameters into this parameter box so that it will be included in the solver wizard. So starting with this one, where, so this is control point 0. Just rename it for a better understanding, so that it will be easier for you to do the, so control point 1. So control point 2, control point 3, and then control point 4. So now we have included all the parameters into the parameter section of the solver wizard. Next, you can go to the execution tab, and you can see which is the product that it's going to work along with, which is nothing but Speos, the latest version, and then Speos simulations. So which is actually to be exported, nothing but the light guide for within the Speos simulations. In the export, like, you can also check which format it has to be exported. So by general, it will be like Speos format, like SC docs format, and you can also use another format as well. Like along with the SC docs, it will also create a different format. But now we are going to use the everything default settings. So click on next. So now you have to keep a certain range. So we will be keeping a certain range. So I'm going to keep a range 50 to 100. So now the value is 70, but it has to, while optimizing or doing the sensitivity analysis, it has to go between 50 and 70. So that is what I'm telling here. So 50 and 100. So it will go between 50 and 100. And for the control point 3, it has to go between 30 and 80. And then 0 and 50. So these are the ranges that I'm going to set for the parameter. I'm parameterizing these inputs. So click on next. Now you can see the responses. So based on these responses, we'll be creating a criteria to optimize as well as do the sensitivity analysis for our structure, for our design. So now we are not going to do it. We are just going to create the workflow. Now click on next. Now you can create a template name, which is nothing but it's a headlamp light guide. So now this is the workflow. Now this is the light guide. So from here, like, you'll get the inputs to the Speos core, and then again you'll get the Speos output, and again it will feed into it like continuously based on the different designs. But this is the workflow. Now what I'm going to do is, in order to so in the Speos output, you will get the results in the format of XMP. Now I want to see the results in the format of like PNG or something like that. So for that, I'm going to use a Python code. So if you click the module, you can see the Python. So I'm just going to drag it here. Now you can see. So if you double click on this, you have the you can edit all these things, common settings, and if you click on it, you can edit these particular settings as well. So now I'm going to check everything. So headlamp, like, we have added the parameters and all, so that is fine. Now check the Speos code. Now you can see this is the Speos core path, and then you can define which one you will be using to run the Speos simulations. Like either you can use the GPU solver, or else like you can use the number of cores as well. Like let's say now it is 1 by default. You can also increase the number of cores to 10, 8, like based on the availability as well as the license capability. Let's be 1 as well. Like I'll be keeping the default one only, and then click on OK, and then go to the Speos output. So in the Speos output, you need to feed the input values. So here you can see the Speos isolated files where you can find this light guide report, where you can take the results like average value. So rename it to average, and then RMS contrast, RMS. Let's take maximum and minimum. Let's see what is the maximum and minimum value as well at the end. So and then minimum, and then I need to add a rule as well. So let's say the number of rules failed. Number of rules failed. Okay, that's it. So these are the outputs. So this is the outputs that I'm going to taken care of, and if you click on it. So we have imported the model, but we haven't used any Python file. Let's navigate. So we have a Python file like this, which we have already written the code. You can also write a different code as well. If you open it, you can see. So this is the code, like it will see the XMP file and it will convert these XMP files into PNG format. So that's what it will do. So that's it. Now we have set up a complete workflow. Okay. So you can just click on it to run to check the workflow, or that is the first thing. So the next thing is once the workflow is done, what you can do is you can add another wizard like sensitivity wizard to analyze your sensitivity analysis. So first I'm going to click on it, but it will take a time, like whenever I'm so it will check the things and all. So it will while running this one, it will initially create a design. That's it. So while creating a design, it will run the things here. It will come to the Speos core and then Speos output, and then we'll get an output in the format of Python. We can see the output as well here. So once this is done, what we will be doing is we'll be seeing how to add the sensitivity wizard and all. So I think it is taking some time. Let's wait for 2 minutes. It probably take 2 to 3 minutes. So that is why like we cannot do the live demos. Like I mean, we cannot now you can see it has been passed. So if it is passed, like everything is fine, the workflow is fine. So it will give you a symbol like this. If it is not, so you need to troubleshoot it. So most of the troubleshooting problem will be based on the directory. So whenever you are working in optiSLang, so it will create a separate folder called Speos isolated files to access the Speos output. So so if the folder is not created, if you're directly taking the files from a different folder, the Speos output files folder, so at that time it can cause some problems. So you need to change the folder to get the results. And in the Speos output, sometimes it won't be reading the that HTML file properly. So that is one thing. And in the Python code, like, so all these things would be mostly really into the working directory only. So you can just check on it and you can understand it later. So this is the so now the simulation has been done. Now let's see core is doing it. So once it is done, Speos outputs will be there, and then the Python code will create a XMP file. So after this, we will see how to do the sensitivity analysis, and then how to analyze the results in the sensitivity analysis, and then we'll be seeing how to optimize it. So mostly we do not have enough time to show the demonstration, because like whenever we are doing the sensitivity analysis, it will create 200 designs by default. So if I have to run it 200 designs, it will take probably 3 minutes, like 4 minutes for a single design. So obviously 4 into 200, yeah, it is too much. And similarly in optimization, by default, it will create 4,000 designs. So by default, it will create 4,000 designs, but I'll show you, we have already those results. I'll show you the results, and based on it, like we can analyze it. Okay. So, but let this run only. So after this, like we'll be focusing on like the files which are being saved. Also, by default, I have selected only one core. So what I can do is, like if you have more number of cores, and if your license is having the capability to access more number of cores, we can increase the number of cores in the Speos core settings as well. So by doing so, it will reduce the simulation time. Also, like if you can also change it to GPU computation. So by doing so, it will also reduce the simulation time. I hope it will be done. So once it is done, I'll show you how to add the sensitivity analysis workflow. And after that, how to add the optimization analysis workflow. Let's stop. This is taking too much time. I'll let you know how to. So now, so this is the setup. So sorry, just it is taking more time, so we do not have enough time. So what I'll do is, like, once you have set up the workflow, just click on execute button. So to check whether the workflow is fine. So since I have cut it in between, so it is throwing an error like this because I have stopped it. So it will take some time. So you can see the state. If you click on the status overview, you can see this as well. So all these things will be green. If it is green, so whatever the workflow that you have set, it has no problem at all. So next you move on to the another thing, which is nothing but tree sensitivity analysis. So now if I click on this, so drag and drop on here. So see, now I have the sensitivities on. So this is the dialog box. So I'm going to keep the ranges like this and click on next. Now I'm going to add some criteria like, so I'm going to add the criteria based on average. So my average has to be the maximum. So that will be my objective, not the constraint. So it will be maximize. So that's it. And then my RMS value that has to be minimum. That is also again objective. So I'll keep it minimize. And then the number of rules failed. So that is the constraint. So it should be 0, but the limit we cannot set it 0. So that's why we're keeping it a value between 0 and 1, that is 0.999. That's it. So these are my, if you look at this, these are the, so these are the responses that we have taken for criteria. So we have two objectives as of now. So based on these two objectives, we'll be running the sensitivity analysis. So by default, it will give the different sampling method based on our design. So as of now, like, we'll be taking this AMOP sampling method and click on next and click on finish. Yeah, now you can see the AMOP. This is the sensitivity analysis tool. So what it will do is, like, it will do the sensitivity analysis and then finally you can analyze the sensitivity results. And then let's say you once you have done the sensitivity analysis, like, you can also double click on it to change the criteria. So now you can see by default it shows, like, by default it will run the 300 samples by default. Like, minimum it has to be 100 to get you at least the results. So this is the criteria. So as of now, like, we do not have any designs. So the number of designs you can see it here, like, once the simulation has been run, and the adaptation 300, and so other designs, like how the post-processing files has to be, like, it has to be images, result designs and all. So you can do all these things. So this is one workflow. So this is for sensitivity analysis. So once the sensitivity analysis is done, now I want to do the optimization. So what you can do is, you can click on the optimization wizard and drag it here. So you can directly use the optimization without using the sensitivity as well. So it's up to you. But this time, so we have two objectives. So let's say I have the next. Let's say it is creating, yeah. So the optimization. So I'm going to use the MOP solver. So it will be like a one-click optimization. So I'll be using a, so now you can see the number of design evaluation. So it will evaluate nearly 4,000 designs. So we're optimizing it. But since all these things are automated, it is really easy, and you can easily get the parameters for your optimized design, and it will also be having the optimized CAD in your setup as well. So now click on finish. See, now this is the one-click optimization. So we have a MOP solver and designs. So this is the next workflow. Like, once I have optimized it, so it will take the designs, filter out the designs based on this one sensitivity analysis. and it will filter the designs like around like 20 designs. So it will generate 4,000 designs here, and it will filter nearly 20 designs here, and then it will validate those designs. And based on that, by post-processing it, you can identify which is the best design that it will give you. Okay, so this is the process. So, but here, let's say we have created single objective, right? So multi-objective. Let's say I want to do different single objective. So what I can do is I can go to the criteria here. So I'll be focusing on only RMS. What I can do is I can change this objective type to constraint. So if I click on constraint, just a moment. Yeah, now I need to set up a limit. Let's say 1.65 e power 6. Sorry. So now you can see this is the initial average power value, average luminance value. And so my value has to be like this. So these are the two constraints. Now I have only single objective. So this will be single objective optimization if I run now. So if I have multiple objectives, that will be multiple objective optimization. A single objective optimization will be for a final result, like where you will be focusing on only one thing and will be optimizing your design. And similarly, the multiple objective will be like it will give you a different design as well. So this is the complete workflow. So all these workflows are automated. You just need to click on this run button and it will run it on your own. And finally, maybe it may take like based on your computing capability as well as the system capability. Like if if you have access only 4 cores, it will take a lot of time. If you are having a like HPC capability, or else like if you are having other things, so cloud computing capability, it won't take that much time. So with like maybe 5 hours, so to run the complete optimization, you will get the optimized result design as well. And within it one day, like you can even like within a week, you can go for the product development as well. So you can go for the final prototype as well. So that's what this optiSLang can do. So since I have shown you the workflow and how to add the sensitivity wizard and optimization wizard, so we won't be running those things because running will take a lot of time. But I will be showing how to analyze these post-processing analysis. Let's start with this AMOP. AMOP is nothing but like the sensitivity analysis. So the one thing is there, like we have already did one analysis. Like I have done one analysis with minimum number of designs, like 10 designs for sensitivity analysis. So let's go there. So as you can see, whenever you're running the design sensitivity analysis, it will create designs like this. So if you click on each design will be having Speos input files, Speos output files. So like where you will be having all the designs as well. Let me show you over there. So as you can see, so this I have already run it. So here you can see I have created a optiSLang file. Here I have run the sensitivity analysis. In the sensitivity analysis, have ran it with 10 designs, like for a time being. So in the 10 designs, you can see each and every design is having this light guide. So these are like different parameters, like the one which you had actually. So initially we had certain parameters, right? So these are the optimized designs. So if you click on it, you can get access to the CAD as well. So now this CAD is actually have a different parameters. Similarly, each and every design is having a different. So it has a number, right? Like 1, 2, 3 and all. So it has an ID as well. So if you're designing 4,000 designs, it will give the design number as well. So based on these folder, you can able to access the design, the optimized design, and you can finally also analyze the results as well. So that is one thing. So that you can do. So now I have ran for like 10 designs. So let's open this particular file. So PD, OP. These are the monitoring databases. Let me open it. So let it open. Yes. So now it has opened. So now you can see these are the COP matrix and all. Like now you can see each and every designs. So now I have selected a design 5, and here if I click on use current design values, you can see for the design 5, these are the values. And if I go to the Windows, if I click on files, So I'll be focusing on light gate radiance, right? So this is the PNG. So based on the XMP, folder that we have added, like, so for the design number 5, we got the radiance like this. Now I'm going to select a design 8. Now you can see the this thing have changed. Now let's say I'm going to select another design. Now you can please closely observe. You can see the changes. So this is how you can see the results in real time as well. And let's say I have selected the design. I want to see the parameters that we have optimized. So this is the optimized parameter, the control points, different control points that we had, right? So for all the 5 control points, this is the value. So if you go and check your CAD, the design number 7, so this will be the value. So the CAD values will be having this. So this is how the optiSLang is doing the sensitivity analysis. So the sensitivity analysis will give you best design, and based on this, like, you can go for it. So this is, we have run only 10 designs. Now we have already one file, like where we have ran for like nearly like so here we have ran it for nearly 200 designs. So now you can see here. So these are all the values. Like if you look at this response plot, these are the visuals. Here you can see response surface 3D plot. You can drag it here and you can see this. So this is the linear regression for like only based on RMS contrast. So here you can see the RMS contrast is maximum for this particular design. And then like, so the best design could be this one, the design number 126. So where we are having a very less RMS contrast. Yes. So below that, like, I think we are having this one. So 51. The design 51 could be the one which is having a very uh, less contrast. Like for this one, like I want to see the design values. Let's see. Yeah. So now I can see the parameters value as well. And the another way to identify is the COP matrix. Here also you can see. So the RMS contrast. So the control point 1, 2, 3, all these are giving some contributions, but the control point 4 and 5 have negligible impact on this RMS contrast. Similarly, if you're taking average, so apart from control point 3, all these are having minimum impact, but all the points are having an impact on average. So based on that, you can identify like which parameters having which what kind of impact on the objective that we are having. So this is how to do the analysis and all. Let's see visuals and all. So this is how you can do this, like analyze the sensitivity analysis mostly. And based on this, like you will be having an different method as well. Like let's see some other. So each and every visuals is having a different name. So based on this, you can able to identify the different design. Here also you can compare the design as well, like based on the criteria, like based on the number of designs. So design 199. So 199 designs are there. So based on this, like can identify it. And there is one more path actually. Let me try to identify that one, like so that it will allow you to like clearly understand that particular one. So here you can see there is one thing called parallel coordinate pads. So if you click it, so if you look at this image, you can see different all these curves represents different designs with the corresponding TP like control points, as well as the 5 responses that we have taken: average, minimum, number of rules that it has to pass, limited, RMS, contrast, and all. So the maximum it achieved is around like 19,000 average of 190 kilo candela per meter square, and the minimum RMS contrast that it has achieved is around like 0.21. Okay, so let's say I want a RMS contrast which is very much low. Let's go here. So now you can see it will filter the design. Now I come to a design. So which is the design number 51. So the design number 51 is actually having a very less RMS, but you can see there is a trade-off. So the objective, like the average value that you have is it's very low, not like it's kind of low, it's not like maximum. So what you can do is the average, so that is actually a trade-off between the average as well as the RMS contrast. So let's say I want to have a design which is having a maximum RMS, sorry, to keep the RMS like this, let it be like this. And if you see the maximum, sorry, objective, not this one. There is one design. Okay, there are no designs actually. So far, like satisfying both the conditions, we do not have like any designs like this. So this is how this is one way you can understand, like by using these sliders and all, like you can understand your designs and all, like how you can identify which design is having a better RMS contrast or something like this. So all these will be having an identity numbers, and these numbers are corresponding to the design folder. So you can go to the folders over there and you can check the CAD as well. And in the parameters value, once you have selected the design, if you click the use current design values, it will give you the corresponding input parameters that you have taken for the optimization. So this is for doing the sensitivity analysis. So in the same way, like I have shown you the workflow for the optimization. So once you have done the optimization, you need to do the post processing as well. So let me open one optimization that we have done already. So this is the optimization. This is before validation. Like while doing the optimization, it didn't do the validation. So before validation, what is the optimization result? So it has selected one design, which is the number 3996. So for this, these are the parameter control points that you are having. See, these are the parameter control points. And then it achieved a criteria base, like no rules has been failed. Okay. So the RMS contrast is 0.36 and the objective, like the average is 185 kilo candela per meter square. So it has passed all the values as well. So the response data here, the criteria is also passed and the response data is also like this. We got the values here and you can see the minimum and the maximum as well. So here from this, you got the values and all. So you can see the design parameters, criteria data, as well as the response value. Okay, now let's open a validated one. Like so now if you look at this one, so here you can see, so all these designs are designs which follow all the rules and all. So no constraints have been violated. Now you can see this is the designs which are having a very good results. These designs, the red color indicates the designs which are having very good designs, and the green which is having a, so totally there are 4,000 designs. So in the 4,000 designs, while doing the validation, once the optimization is done, so the optimization tool, the workflow will validate 20 designs, the best designs. So these are the 20 best designs. So you can see the green color, which is marked by a red, ring. So these are the validated designs. So here you can click on it to understand like what is the number. All these validated designs are here. So what you can do is like you will get the validated designs, results and all. So now based on the design validation and all, so further it has selected a best design. So earlier it was 3996, that is 3996. Now it has selected a design which has a best average value, but has an RMS contrast, the criteria data. But this time we have a little bit higher, RMS contrast. So based on this, it has created one distance like data. So this another for like validation. So further, this both are like multiple objectives. We have two objectives, right? So average as well as the RMS contrast. So the next thing will be how to analyze a single objective thing. Like we have it as well. So here you can see, if you look at this objective history, so all these graphs are designs. So the only objective is RMS contrast. Okay, so the designs are being optimized. So you can see, so we are having a different RMS contrast for different designs. And after one point, after 274, you can see the RMS contrast, you do not have a very huge value in changes, which means they're converging. So they are like converging. So nearly closer. The RMS contrast value lies between 0.2 to between 0. So we are achieving a very good results after this. So based on these, our design, based on these criteria and all, it has selected a best design, which is 370. So the design number 370 is having a minimum value of 11407. Sorry, the RMS contrast value of 0.114. And then these are all the design parameters value. So you can go to the design number 370. And if you check the CAD data, the control points will be these values. And if you check the results, like the radiance as well as the intensity, you will be having these values as the RMS contrast and all these values. So use current design values. You can see the control points has been updated here as well. So this is how the optiSLang is optimization is done. Like let's go back to the results as well. Here you can see while doing the optimization, you have like this is with the multi-objective where we achieved different things. But here you will be having a best design with single objective optimization, like where you have achieved a results with the RMS contrast of 0.115. Okay, so that's how you can do the optimization. And if you go back, you can find, like as I told, like you will be having a different folders, like it will create automatically in this folder, Lightguide folder, like that optiSLang folder, it will create n number of designs. And if you look at this message log, it will tell you like how the complete workflow, it will show like what it happened, like how it is designed and all. So in this design, like you can understand, like every results will be having a Speos output files where you can go and check the results and all. Sorry, Speos oscillated files. It will be having all the things. So based on this, that Python code, it is actually giving us a intensity radiance file as well. So this is how you can see. So let's see one thing. Since this is our basic design, right? Like let's go back. So this is the basic design without any optimization, right? So let's go there and let's get the radiance data from there. And we already know the best designs parameters value. Okay, parameters value, we have taken it from there. And what we will do is we'll try to change the parameters here in this, and we'll try to optimize it. So give it some time to load. Okay, sorry, it has been already there. See now, this is the basic design, the design that we started initially. Okay. So now it has the control points value like at 0.70. These are the initial values. For this, I have this radiance. So I'm going to, so if I click on this measures, I can see the values and all, RMS value and all. And then if I click this, I can see the intensity and all. Now, based on the best optimized design for a RMS contrast, good RMS contrast, and achieve the uniformity is design number 370. That's what we got it from here. The best design is 370. So now we have the design values here as well, the design parameters. What we will be doing is, so let's save this file separately, like for a post-processing analysis. Like today, I'm going to save this. So light radiance without optimization. So let's say it's somewhere where we can easily analyze, like take it like, okay. So I have saved it. So this is without optimization. Now let's close it. Now the design number is 370 and we have the constraint parameters. So sorry, the optimized parameters. So let's note it down. So I'm just noting it down like 85.3106. So yes, so now we'll be using these design parameters, the optimized design parameters in my design. So go to the light guide. So design, light guide. I'm going to change the value. So the 0%, which refers to control point 1. So that value is 92.66, 90, sorry, 90. Just a moment. Okay, sorry, something wrong with the file. So let me reopen it. It is not allowing me to change it. So I have already one file which is open. Let's go to the design here. .92.66 6609. that is control point 1 value, and then 85.3106 value 06, then control point 3, which is 79.6948, then control point 4, which is 67.1027, and then 15.6894. So now we have added the best design values. So what we will be doing is we'll click on compute. So it will recreate the waveguide based on the new control points, the best design values, and then we'll again run the simulation. After that, we'll compare those two results to give you a best idea how optiSLang optimized your design. Now go to the simulation, click on light guide. So let's compute. It won't take more than 30 seconds. So let it simulate. Yes, now done. So let's go to this radiance. So both the designs, you can see all the rules has been passed. So click on the radiance. Now I'm going to save as. So light guide radiance. So this we have already without optimization. What is the result? And now I'm going to add optimized. So now we have two results. Okay, let's go there. Let's get these results. Go to the desktop. So let's open first without optimization. Yes, and then optimized one. So we will the goal is to achieve the best uniformity, right? So that's it. So this one is optimized, and this one is. And now you can see, like from this itself, you can see there is a uniformity on the right hand side. So which is actually the optimized one. So on your left hand side, the initial design, which doesn't have any uniformity. So if you click on measures, you can see the RMS values and all for this particular one. So RMS contrast. So for this design, like see for this design. So what is the RMS contrast? So this is the initial value. Now if I click on this one, now you can see from this section, you can see like there is no uniformity. But now click on this measures. Now so now compare this. See, we have achieved a very less RMS contrast value. So that was our single objective. So we have achieved it. So earlier it was 0.75 and it was 0.125. And the next thing is we have to achieve the uniformity by doing so. And look at this. So we have achieved a uniform like around 200K, nearly like 183 candela per meter square, like achieved the like average one, like it's nearly like 1600, right? It is not the, here you can see at all the points it is uniform. So here if you look at this, here at near to zero, it is very high. So from this we can understand how, so now you got to know like how the optiSLang is being used for optimizing your design. So this is for a simple light gate design. So in the same way, you can able to optimize different optical designs using Speos and also coupling along with the optiSLang. So I hope like this gives you a better idea like how to use optiSLang. And look at this also, like the initial design is like this and the best design. So this is what we have achieved here. Here, this is the design that we have achieved here. You can look at these designs as well, like initial design, the best design and all. So the RMS contrast, like we achieved around these things. So this is the summary. Due to the sensitivity analysis and optimization, so the best possible trade-off between the RMS contrast and the luminance can be found. Homogeneous lit appearance. Actually, we have improved it significantly, like at the best design. Like there is the homogeneous lit appearance, and all the photometric regulations are being passed. None of the regulations has failed while doing the complete optimization. So that is the other things. So what we did is we have kept all these constraints in check and we have achieved our objective as well by doing this optimization. And this is all about the webinar today. So thank you.